So hello students, in one of our videos we had discussed about the working of a half wave rectifier circuit. Okay, so this is the circuit of a half wave rectifier with input Vi is equal to Vm sine omega of t. The output looks like this. Okay, so to summarize, in a half wave rectifier circuit, the diode conducts for only one cycle. Okay, so depending upon the position of the diode, in this case the diode conducts in the positive half cycle of the input, whereas during the negative half cycle we do not have any output. Okay, the diode does not conduct. And we had also looked at the different performance parameters. So VDC can be expressed as Vm upon pi. VRMS, which is root mean square value, is Vm upon 2. Ripple factor is 1.21. The efficiency of a half wave rectifier is 40.6%, and the peak inverse voltage is equal to Vm. Fine. Okay, so today let us try to look at how do we arrive at the VDC and VRMS expressions of a half wave rectifier circuit. So we will try to derive it. Okay, so you can very clearly see the input as well as the output waveforms. So V output V naught, which is varying with respect to time based upon the waveforms, it can be written as V naught of t is equal to Vm sine omega of t when t is in between 0 to t by 2, and the output V naught of t is 0 when the time t is in between the period t by 2 and t. Okay, so what does this mean? The output appears only between 0 to t by 2, whereas from t by 2 to t there is no output. The output is 0. Okay, so here the capital T represents the period. Okay, fine. So now let's try to understand what do we mean by VDC. VDC is nothing but the average voltage that is appearing at the output side in the positive as well as negative cycle. So if I consider both the positive as well as negative cycle, roughly I'll be getting the average voltage or VDC voltage somewhere in this range. Okay, so let me just express it as VDC. Please note that VDC is nothing but the average voltage that is appearing at the output side. Fine. So mathematically if we start to derive it, well, this is how it goes. VDC is equal to, because it is the average value, we'll have to write it in this way: 1 upon T integration of sine omega of t, which is multiplied by Vm. Okay, so what is Vm? Vm is the maximum peak voltage. Okay, so this is integration of Vm sine omega of t dt with the limits, integral limits from 0 to t. Okay, so initially we'll have to consider the entire period from 0 to t. Now however, we do not have any output from t by 2 to t. We have the output only from 0 to t by 2. So we can simplify this expression as 1 upon t 0 to t by 2 Vm sine omega of t dt. right? Further, so if I take Vm outside, Vm is a constant voltage, so I can take it outside the integral sign. Vm upon T, integration of 0 to T by 2 sine omega of T dt. So what is integration of sine omega of T? Integration of sine omega of T is minus cos omega T by omega. So this is Vm upon T. Integration of sine omega of T is cos omega of T upon omega with a minus sign. So minus I will be expressing it outside. So the limits will be 0 to T by 2. Now what is omega? Omega is the angular frequency which can be expressed as 2 pi by T. Okay. So if I just take it outside, I will be getting minus Vm upon T. Omega is 2 pi by T. So T gets cancelled, and in the brackets it will be cos of omega is again 2 pi by T, and substituting the limits for T by 2 and minus of cos 0. So this is what we will be getting. So T gets cancelled, 2, right? So what is cos of pi? Cos of pi is minus 1. Cos of 0 is 1. So this will be minus of 1, right? And outside it is minus Vm upon 2 pi. Okay. So if I simplify it, the expression that I will be getting it, minus into minus, it will be plus. So it is 2 Vm upon 2 pi. So 2 gets cancelled, and I will be left with Vm upon pi. Okay. So the expression for VDC is Vm upon pi. Let me just write it here separately. VDC, or the V average value of a half wave rectifier, is Vm upon pi. Right? Okay. So that's very simple. So the steps are similar again. So how can I express V naught of T? V naught of T is Vm sine omega of T for T in between 0 to T by 2. Similarly, the output is 0 between T by 2 and T. Okay. Now, as far as the expression for VRMS goes, how can I express VRMS? See, RMS stands for RMS. The full form is root mean square. Okay. So let me just write the expression for RMS voltage. VRMS. Okay. So VRMS can be written as root. Okay. So I'll have to take the root first, then mean. Okay. So for a half wave rectifier, if I want to take the mean, that means when does the cycle repeat? Okay, whether the cycle repeats from 0 to T by 2 or 0 to T. Okay, so it is from 0 to T. So for 0 to T, the cycle just keeps on repeating. So I'll have to consider 1 by t integral from 0 to t by 2. Okay, because the output is appearing only from 0 to t by 2. However, the period or the cycle is from 0 to t. Okay, because the cycle is from 0 to t, I am considering it as 1 upon t, whereas the output is appearing only from 0 to t by 2. So this is, the integral is 0 to t by 2. Okay, because from t by 2 to t there is no output. So then the square, Vm square sine square omega of t, omega of t. Okay, fine, dt, omega of t dt, right? So if I start integrate it, let's just see what do we get. Now we have sine square omega of t. Okay, so what we will do now is, just to simplify the things, let's try to take it as v square RMS. Okay, so when I take square of RMS, this square root on the right hand side will go off, so it is 1 upon t. Vm square is a constant, so let me take it outside the integral, right? Vm square, and it will be 0 to t by 2 sine square omega of t dt. Okay, now how can I express sine square omega of t? See, we know that sine square 2x can be represented as, okay, 1 minus cos 2x upon 2, right? So with respect to the integral formulas, we know this expression. Okay, so substituting the same thing over here, it is Vm square upon t 1 minus cos 2 omega t by 2, integral of 0 to t by 2 dt, right? Okay, so if I take this 2 outside, then it will be Vm square by 2t, then integration of 0 to t by 2 1 minus cos 2 omega t dt. Okay, so I'll have to continue further. Let's see what do we get. Okay, so if I just start continuing from the previously stopped step, what I'm going to get, which is Vm square upon 2t. What is integration of 1 with respect to the time t? Well, it is t minus, okay, so integration of cos 2 omega t is sine 2 omega t divided by 2 omega, right? I'll have to substitute the limits, so it is 0 to t by 2, 0 to t by 2. Okay, right. Then Vm square by 2t, let me just keep it as it is. So this is, when I substitute the limits, I will be getting t by 2 minus, okay, so this is 1 upon 2 omega, omega is 2 pi by t. Okay, now sine 2 omega of t. If I just substitute, it will be sine of 2 pi by t omega, and in place of t, if I substitute, t by 2. Okay, next minus of 0, so this is sine of 0. Okay, now if we closely observe, it is seen that t gets cancelled. Okay, 2 gets cancelled. So what is sine of pi? Well, sine of pi is 0. Similarly, sine of 0 is also 0. Okay, so what will be the net result? This entire term becomes 0. So what am I left with? I am left with Vm square upon 2t t by 2. So t gets cancelled. I'll be getting Vm square upon 4. Okay, now this is V square RMS, right? So if I want VRMS, I'll have to take the square root of it. Square root of Vm square upon 4, which is Vm upon 2. Okay, so finally we arrive at the expression VRMS is equal to Vm upon 2. Okay, so today we have seen how to obtain the expression for VDC and VRMS of a half wave rectifier circuit. In our next video, we will try to look at how do we obtain the expressions for a full wave rectifier circuit. So I hope students have understood this concept. Thank you very much.